start. So how
They're both really good. I mean, the French and Dutch pronunciation, you've mastered them both. So the name was well pronounced. I should point out that I'm not professor. I've kind of not contradicted anyone so far because I like the title on my office. But now that this is being videotaped, I should point it out. Okay, so I'll start just by giving a brief overview of what I intend to talk about. So, first section, I want to introduce the two main characters of the story, so which are the perplectic Lie superalgebra, PEN, and the perplectic Brouwer algebra, noted by AR. Then I'll go into the representation theory of the Brouwer type algebra. Then I'll mention the representation theory or some facts about representation theory for the perplectic Lie superalgebra. So in particular with focus on what can be obtained by the study of this algebra, but also links with some other recent results. And finally I'll talk about the Bilinear category. So those are the 4 sections, so they probably will coincide more or less with the 4 days, but I can't promise that it will be exactly matching. These 3 sections are about new results, which can be found in 3 archive preprints. I'll just give them here. So these last 2 are joint work with Michael Erich. Okay, and let me also just immediately say that everything I will say is over the field of complex numbers. So a lot of things can be dealt with in greater generality, and a lot of new features appear which are interesting in their own rights, but I think probably it's best to just focus on that case rather than having to specifying all the time what is being considered. Okay, so then the first section. So I'll start by sketching briefly the situation of the perplectic Lie superalgebra as an element of what is known as the classical Lie superalgebras. So I assume that people know what a Lie superalgebra is. So then a finite dimensional Lie superalgebra, let's say G, which is direct sum of the even and the odd part, is classical if, first of all, the underlying Lie algebra G0 is reductive, and the adjoint representation coming from the definition of a Lie superalgebra of G0 on G1 is semi-simple. So G1 is semi-simple as a G0 module. So with these definitions, there's still a lot of algebras which satisfy these conditions. I mean, the recipe is you start from a reductive Lie algebra, you take some semi-simple finite-dimensional module, and then what's left is to find some pairing between G1 and G1 going to G0, which is compatible with everything. So there's still a lot of freedom to construct things, but what we're interested in, what many people are interested in, is the simple ones. So the simple Lie algebras which satisfy these properties, and to be more correct and less specific, the ones that are close to being simple. But so the simple ones have been classified. So the classification was finished by Victor Katz in the 70s, I think. So classification of the simple classical Lie superalgebras. Given by this list. So I'll explain what most of them look like in a second. So I should also point out that many people find the way that I write M and N confusing. So this is an attempt to write these two letters. So according to many people, a failed attempt, but I hope it's somehow clear, and I'll avoid using M and N too much later on, but these are the standard letters to be used here. So there's also a bit of different possibilities for notation in use. So these two are sometimes just written as a capital Pn or capital Qn. And these are also known as A, and these as B and C. But yeah, I'll just stick to this notation for now. And of course, any simple Lie algebra is an example of a simple classical Lie superalgebra. Okay, so I'll come to what I'll mention what these are now. So these are a couple of exceptional cases. This is a one-parameter deformation of a special case of this Lie algebra. So I'll talk a little bit about these one here, the discrete parameter families. So I'll just briefly mention by a supervector space, I just mean a Z2 graded vector space over the complex numbers. So just this space which is spanned by two subspaces, one you assign to be even, one odd. And I need the notation that for an element of V0, I write that V between two lines is 0 and 1 if it is odd. So So whenever for an element of a supervector space I write this, I assume that it is actually homogeneous, so that it either belongs to V0 or V1. And this is what it means precisely. So if it is finite dimensional, then of course usually we'll use this notation with m the dimension of V0 and n the dimension of V1. So then the first Lie superalgebra I want to mention is GLMN, which has a vector space, or better as a supervector space, is given by the endomorphisms of CMN. So this just corresponds to the space of m plus n by n plus n matrices, where we have some Z2 grading, which is inherited from the grading on here. So typically we could write these matrices in block form, using m by n and n by n blocks for A and D. And then of course the even part is formed by these two blocks and the odd part by these two blocks, because these blocks will exchange the parity of this vector space when they act on it. Whereas this maps even to even and this maps odd to odd, so as morphisms they are both even. So then the first one, which is actually in the list, SLMN, so just already for the algebras, you'll have that this isn't simple. So the simple subalgebra is given by the matrices which have zero supertrace, which just here means that the trace of A and D are the same. So that's the first one in the list. Then when m and n happen to coincide, there's actually a different one which is simple, because if m and n are the same, then I could still take the identity matrix for A and D, and they would have identical trace because their dimensions agree. And that one is obviously in the center, so you need to quotient it out, and then you get PSLNN. But often people just study GL or SL and don't worry too much about PSL, because then stuff follows from that usually quite easily. So that's what I mean by we're interested in Lie superalgebras which are close to the simple ones. Okay, to construct some other Lie superalgebras in the list, we'll now take some bilinear forms on this initial supervector space. Maybe I should mention the product on this algebra. So I've given it as a supervector space. The product is, or the Lie super bracket, is then given by the super commutator. So this is an instance where, in order for this to make sense, we need to assume that they're both homogeneous, but then we extend the definition by linearity. So it's just the ordinary commutator up to a potential sign when we exchange two things which are odd. So now we take some bilinear forms. Which we assume to be supersymmetric. So by supersymmetric, I basically mean that if you exchange the two entries, you should get the same thing up to potentially a minus sign when you exchange two odd things. So it always is the same type of ID. So often we should just say symmetric and assume that we work in the supersetting. And non-degenerate in the ordinary sense. So then there are two things we could do. We could, for instance, first assume that this form is even. So by which I mean that evaluating on U and V should give 0 unless they're of the same parity. So in other words, it doesn't see the even and the odd part of the vector space don't see each other. So in particular, this form restricts to a symmetric form on V0 or Cm, and to a skew symmetric form on V1. So the odd part of the vector space. So in particular, this forces n to be even. Otherwise, I couldn't have a skew-symmetric non-degenerate form on V1. So n is, of course, a dimension of V1. So using this form, I can define this Lie superalgebra OSP n to n. So 2n because n is even, so we might as well write it as 2 something. But so with this convention here, this superalgebra is defined as the subalgebra of GLMN, for which this relation holds. For all elements U and V in the vector space. So in particular, if n would be 0, we just get SP. If n would be 0, we just get the orthogonal Lie algebra. And this is kind of a generalization of both at the same time. So the case that we'll be dealing with in this mini course is not when the form is even, but when it is odd. So that means that the form vanishes unless the parities add up to 1. So now, if you would restrict the form to V0, it would be 0. If you restrict it to V1, it will be 0. We actually just get a pairing between V0 and V1. So we get a non-degenerate pairing of V0 and V1, which of course now forces the dimension of V0 and V1 to be the same. But so when we have such an odd form, non-degenerate supersymmetric on C, let's say N, then we can define the paraplectically superalgebra, which will be at the center of this mini course. So then that's just defined in the same way as OSP, namely the subalgebra of GLNN of elements which satisfy this relation. So, to make it more explicit, the canonical choice, or a canonical choice, for such a bilinear form leads to a matrix realization of this algebra. Like this. So A is arbitrary, we've got n by n blocks. So B is symmetric and C is Q-symmetric. That's an explicit realization of this algebra. So then we get to one which is sometimes denoted like as PEN, sometimes as capital P tilde as well. So that's not yet the one in the list, this one here, because it turns out that the derived E superalgebra is a different one, and that one is the one in the list. So in this realization it would be given by all matrices like this, with the additional assumption that the trace of A vanishes. So then this one is simple. But again, for the rest of the talks, I'll focus on that one. Okay, so you've already seen that one, that one, that one, and this one. So to complete the discrete parameter families, I'll just briefly mention what that one is. So the Lie superalgebra Qn is also a subalgebra of one of the GL, the general linear superalgebras. It's given as the elements which commute with some algebra. So again, we have a supervector space with even an odd subspace of the same dimension, and well, let's just say phi CL. I've misread my own CL as a phi. Can't be good. It's a two-dimensional Clifford algebra. So it has identity and E, where E squares to 1. And E is given as an odd endomorphism of this space. For instance, this matrix realization. So Qn is then everything which commutes with that subalgebra, so which commutes with this operator which just exchanges the even and the odd part. So in matrix realization, would then get all the matrices of this form. So again, this one isn't simple, and then you need to perform some manipulations, take some subalgebra, quotient out some one-dimensional ideal, and then you get the simple one, which is in the list. So these last two that I've introduced, P and Q, are often called strange. So there's a couple of good reasons for that. First of all, there's no classical version. So there's no Lie algebra. Of course, classical is a bad word because I just said they're classically superalgebras. But there's no Lie algebra version. For the GL or OSP, it's clear that they generalize some Lie algebra. So this is not the case here. This is something fundamentally new. So could say that they're truly super in some sense, even more super than the others. By which I mean, when we constructed GL or OSP, we performed a classical operation on a supervector space. We just took all the endomorphisms of a supervector space, or whatever is preserved by some even form. Whereas for P and Q, we do some super operation on a supervector space. We take an odd form, or we take a morphism which exchanges even and odd stuff. So they're somehow superalgebras of the second generation, you might say. So that's not just some philosophical nonsense. It means that we'll get new algebras in their invariant theory. So the invariant theory of GLMN or OSP is controlled by classical algebras as the symmetric group, its group algebra, or the Brouwer algebra, the Wald-Brouwer algebra. Whereas for P and Q, you get some new algebras. So the paraplectic Brouwer algebra that I'll mention in a lot of detail, and for Qn, an algebra known as the Sergeev algebra. So really some new algebras. And another reason that they're strange is their triangular decompositions. So these classically superalgebras, they admit some version of the triangular decomposition into positive roots, Cartan subalgebra, and negative roots. So for GLMN, one can just take the upper diagonal matrices and the lower diagonal matrices, as in the classical case. But so for P and Q, these triangular decompositions are somewhat weird or strange. So if you have such a triangular decomposition, then for P, we can't find a triangular decomposition where the dimensions of n plus and n minus agree. So usually one gets a nice pairing between positive and negative roots. So that definitely doesn't happen here. Even worse, there are more positive than negative roots, or more negative than positive roots, depending on your choice. So that's something quite strange. And for Qn, the Cartan subalgebra is not even, for starters. So for all other cases, H is an entirely even subalgebra. So I can just perform the usual IDs of weights, etc. So for Qn, it's not even, and it's also not abelian. So that complicates matters in a different way. So for the other least superalgebras in the list, their triangular decomposition is somewhat classical. But for these two cases, some weird things happen. Okay, so that was just the first part to kind of situate the paraplectic Lie superalgebra inside the class of classical Lie superalgebras. I don't know if there are any questions at this point. No? Okay. So then I'll move on to introduce the invariant theory for the paraplectic Lie superalgebra. So I'll try to give a complete overview of what's been done. But I won't take a historically correct ordering of results. I'll just try to be complete. So for now we'll just fix V to be this complex supervector space, C and N. So now these are meant to be the same, in case you're wondering. Some odd form, so still symmetric, non-degenerate, and then we consider G, the Lie superalgebra that we'll work with, is the paraplectic Lie superalgebra, so given by the paraplectic Lie superalgebra corresponding to this vector space and the form. So then this space also becomes the natural representation of the paraplectic Lie superalgebra. So the first result I want to mention is what is known as the first fundamental theorem. Of invariant theory. So it's a rather recent result, 2015, by Pierre Bilinear, Gustav Lehrer, and Rubin Zhang. So the theorem states that the space of invariant functionals on the rth tensor power of the natural representation. The universal enveloping algebra of a Lie superalgebra is some kind of Hopf algebra, Hopf superalgebra, So we have natural action on any tensor products of modules, and in particular on the tensor power. And the first fundamental theorem wants to describe the invariant functionals on this space. So that means this space. Where it's important to point that out, because there are also some different conventions. By this I will really mean all morphisms. So not necessarily parity preserving. So this space is spanned by the following functionals. So I'll introduce functional f of sigma for any sigma, an element of the symmetric group on R symbols SR, defined as follows. Element of, so f of sigma acting on V1 tensor V2, etc., is given by the bilinear form acting on V sigma 1, V sigma 2, and again the bilinear form acting on V sigma 3, V sigma 4, etc., until we reach V sigma R minus 1, V sigma R. So of course what I've written here only makes sense if R is even. So in particular, the space is 0 if R is odd, and if R is even, it is spanned by these functionals. So I just permute the copies of V in whatever order one prefers, and then just pairs things up 2 by 2 using the bilinear form. So it is clear that all such functionals are invariant, I would say. But by definition, the Perplexity superalgebra is the one which preserves this form. What is not clear is that this is exhaustive, that this gives all the invariant functionals. But so that was proved in 2015. So they're not linearly independent. Well, first of all, they're not linearly independent in some obvious way. If I switch these two, I obviously get the same functional. But that's not all. If R is big, then there are even some less trivial linear dependencies. But to the best of my knowledge, they haven't really been described explicitly. I think I'm sure some people have some good idea, but I don't think it's been written out anywhere. So in principle, I think the relations between these functionals are not in literature, so the second fundamental theorem of invariant theory is still open for this case. Sorry? I'm not sure. Again, it probably depends what you mean by known. But I don't think it's written anywhere. I'm sure that perhaps these people know, but I don't think it's been proved rigorously or written out. Okay, so that's the first thing I wanted to mention about the invariant theory. So that's good, but I think we still want a bit more. Namely, some description some nice description of the G-invariant morphisms, not just between tensor powers in V and the complex numbers, but between different tensor powers. And also composition of morphisms. So by which I mean some description of this space along with a description of what happens if I compose a morphism from VR to VS with one from VS to VT as a morphism from VR to VT. So now you see that I've messed up the chronological order hugely. So now we go back to 2003 already. And there was an interesting, so the first result in this invariant theory due to Django Moon, who introduced the paraplectic Brouwer algebra. So he defined a paraplectic version of the Brouwer algebra. AR. So this algebra was given in terms of generators and relations. Where these resemble very closely the generator and relations for the usual Brouwer algebra up to some signs, minus signs. And then for all n, there is an algebra morphism from this AR to the endomorphism algebra of a tensor power. So to be more precise, to the opposite. So the reason I want to take opposites is it will be convenient to take the left action of G on this tensor power and the right action of this algebra, which centralize each other. So just a detail. So he constructed this algebra along with a morphism like this, and proved that this is actually an isomorphism if R is bounded by n. So let me just stress that this algebra doesn't depend on n. So we get the same algebra for any paraplectic superalgebra. And for any paraplectic superalgebra, we get a morphism like this, which is an isomorphism if the algebra is big enough, basically, or if the tensor power is small enough. This result was generalized in 2014 by John Kujava and his student Ben Tharp. They also provide a description in terms of diagrams, a diagrammatic description of this algebra, and not in terms of generators and relations. And also more generally, they constructed a category. So some diagram category I'll define it more explicitly later on, but first I would want to give the overview of what it does. So some diagram category curly R, which objects are given by the natural numbers. Again, this category doesn't depend on n, but for all n we get a contravariant functor. Fn from this category to the category of tensor powers of the paraplectic D superalgebra. So that's just a category of modules so just the full subcategory of all modules whose objects are just the tensor powers. So in particular, this functor gives morphisms of vector spaces. Like this. As a special case of this, or something included in this category, is if we take the endomorphism algebra inside this category of the object R, so objects are given by natural numbers, then we find that the algebra which they proved is isomorphic to the paraplectic Brauer algebra introduced by John Gomoon. So in particular, now also given a diagrammatic description of this algebra as a special case. So we have such a morphism. Is it an isomorphism or an epimorphism or something? Well, now we can apply the power of such categories together with the result I mentioned first, which historically came last, so after this result, but now I can complete things, I think, more elegantly. So the first observation is that this space as a vector space is isomorphic to this space. I realized I forgot to mention something crucial, the reason why this is true. Yeah. So let me just mention that here. There is an isomorphism between the natural representation and its dual. Again, this is an odd isomorphism. So some people would write some parity reversal functor here to make that clear, but since it will be more convenient to work with odd morphisms all the time, you can just say that it's actually an isomorphism. So, of course, such an isomorphism is inherited from the odd bilinear form. So if we map any element to this functional, we get an isomorphism, which doesn't respect parity because the form is odd. So in particular, we can easily make this identification. And such diagram categories have the nice property that we also get isomorphisms here. Such that this whole thing commutes. And if we then apply the first result I mentioned, so the first fundamental theorem of invariant theory, which will say that this is surjective, we find that this is also surjective. So putting all these things together, we find that this category gives some description of these invariants. In particular, this result also means that this morphism already constructed by Jumbo Moon is actually always an epimorphism. So this category gives a good description of these morphism spaces. Of course, it's surjective and not an isomorphism, but that's logical because this works for any perplexity superalgebra. So it's kind of a limit which surjects onto any perplexity superalgebra, no matter how big it is. So, what's the time? Should we have a break now? Yeah. Oh, this is the end of section 1.2, then I think it's a good